All right, so we are going to finish up chapter 12 today. And we're going to spend a little bit of time talking about residuals. Your book doesn't really cover residuals at all, but there's two problems in your homework that deal with residuals. So we'll talk about residuals and how you can do all of this on your calculator. Your calculator's pretty slick. Okay, so last week, we had started talking about the regression equation. And given a set of data, you can use either Excel or your calculator to model your data to a particular type of model. We're only looking at linear. We're not looking at any other models, but there's certainly exponential models and quadratic models and cubic models and all sorts of models. We're only looking at linear. And so last week we ran the linear regression test on a set of data that you put into your calculator. And then we stored the model equation in our Y1. And it's important that we do that because in just a little bit, when we start calculating residuals, it makes life way easier if you let your calculator calculate the residuals for you. So we're going to do this again. Now, before you run the regression, you should always do a scatter plot before you do anything else. And that's typical of data, period. If you have collected data, your boss is going to want to see a pictorial representation of that data. They're going to ask you for some kind of chart. And when you're comparing two variables to look at their relationship, then you will be graphing a scatter plot, because then you're going to be able to see the relationship between one variable as opposed to the other variable. All right, talked about all that. Now, there is this thing called the correlation coefficient that can tell you how good your model is at fitting your data, or how close it is to fitting your data. And that's a really complicated calculation. That's why we don't do it. When you run the linear regression t-test, it will calculate the correlation coefficient for you. The correlation coefficient, and it's R, is numerical and provides a measure of strength and direction of the linear association between, the independent variable X and the dependent variable Y. What does the value of R tell you? The value of R is always between -1 and +1. The size of the correlation R indicates the strength of your linear relationship. So if you have a value of R that's close to -1 or +1, that's a strong, excuse me, that's a strong linear relationship. If R is 0, there is no linear relationship between your two variables. If R is equal to 1, that's a perfect linear correlation. That's positive, which means that as your independent variable gets bigger, your dependent variable does too. So if you have a strong linear positive correlation, you have something like this. This is when R is positive. And you'll notice that the value of R, or excuse me, the sign of R, corresponds with the sign of your slope. If R is equal to -1, you have a perfect negative correlation. That means as your independent variable gets bigger, your dependent variable gets smaller. That is when R is less than 0. In both cases, all of the original data points lie on a straight line. Of course, in the real world, this wouldn't actually happen. That is, if R is -1 or +1, every data point lies on the regression line. A positive value of R means that when X increases, Y tends to increase. When X decreases, Y tends to decrease. That's a positive correlation. So as X gets bigger, so does Y, or as X gets smaller, so does Y. A negative value of R means that when X increases, Y tends to decrease. So as X gets bigger, Y gets smaller, or Y tends to increase as X gets smaller. The sign of R is the same as the sign of the slope, B of the best fit line. All right, so here are some images of strong positive, strong negative, and then no correlation. So in statistics, we don't deal with lines that have 0 slope. All right, so does correlation mean cause and effect? And the answer is no, not necessarily. It could, but not necessarily. This is real data. And there's a strong positive linear correlation going on here. But what's our data? What's our independent variable? Independent variables along the horizontal axis. So what's on the horizontal axis? Murder rate. The dependent variable that depends on the independent variable is on the vertical axis. What's on the vertical axis? Ice cream sales. And this is real data in New York City. So is ice cream sales dependent on the murder rate in New York City? Is there a cause and effect relationship as the murder rate goes up? Oh, let's go get some ice cream. We just killed somebody. I don't think so. So there is a confounding variable here. There's something else that's affecting both of these things and causing this strong positive correlation. What do you think it is? Summer. So what happens in the summer? People get out and do bad things. People get out and buy ice cream. So if you look at the correlation between the murder rate and ice cream sales, this is a very famous statistics problem because this is real data. But it shows you just because there's a strong correlation between variables does not mean that there's a cause and effect relationship. Okay, if we take our correlation coefficient and we square it, we get what is called the coefficient of determination. It's usually stated as a percent, where the correlation coefficient we usually state as a decimal. It has an interpretation in context of your data. R squared, when expressed as a percent, represents the percent of variation in the dependent variable. That's the predicted variable Y that can be explained by variation in the independent variable, the explanatory variable. using the regression line. 1 minus r squared, when expressed by a percentage, it represents the percent of variation in y that's not explained by the variation in x using the regression line. So there is a certain amount. If you look at your data and you look at the line that you best fits your data, there is going to be variation in the actual data values of your dependent variable from your actual data, and that is derived from your regression line. And so the variation in the y value from your variation line that can't be explained by the variation in x is this coefficient of determination. All right, so the data that we ran the other day, the Lin-Reg t-test on that set of data, we got a line of best fit of negative 173.51 plus 4.83x. And the correlation coefficient that we calculated was 0.6631. And the coefficient of determination was 0.4397, or 44%. So the interpretation of R squared in the context of this example, approximately 44% of the variation in the final exam grades can be explained by the variation in the grades on the third exam using the best fit regression line. Therefore, approximately 56% of the variation in the final exam grades cannot be explained by the variation in the grades on the third exam using the best fit regression line. And that can be seen by the scattering of your data points around your regression line. Now, is 0.66 a good correlation coefficient? Now, I can conduct a test, and we will in a little bit. As a matter of fact, we get a p-value here. So we can compare this p-value to a preset alpha and say, is that correlation coefficient strong enough to say that there's a linear relationship between this data? So we can do that, and we will. Okay, residuals. Residuals are obtained by performing a subtraction. All we must do is subtract the predicted value of y from the observed value of y for a particular x. That's a residual. So y hat is the y value you get from your regression equation. So whenever you calculate your regression equation, if you plug in a value of the independent variable x, the output you get from that regression equation is y hat. So y is the actual y value from your data. And y minus y hat is the residual. The formula for residuals is straightforward. A residual is the observed y minus the predicted y. Residual is y minus y hat. It's important to note that the predicted value comes from your regression line. The observed value comes from your data set. All right, so let's find some residuals. This set of data, by the way, is a homework problem, and all your homework problems have exactly the same set of data. So when we do this problem, we are doing your homework problem together. Okay, so this is section 12.1, 12.3, problem 12, and 12.6, it's problem 1. So the data shows up twice in 2 different problems. So I would like for you to please put this data in your calculator. Do you all have your calculators with you today? So go ahead and put this data in your calculator. I would suggest putting stories in L1 and feet, the height of the building, in L2. So the stories represents how many stories this building is, how many floors, and height is the actual height measurement of the building. So we're going to look to see if there's a linear correlation between the number of stories a building has and its height. And we're going to do all of this on our calculator, the entire problem on the calculator. Whoops, sorry about that, folks. There we go. How we doing? Everybody done? All right, so I'm going to run over to my calculator. And the first thing that I'm going to do is create a scatter plot of that data. All right, so make sure I have my data in there because sometimes my calculator does weird things. It looks like I have it in L1 and L2, so I'm good to go there. So I'm going to do a scatter plot of L1 and L2. So I'm going to go second stat plot, and I'm going to make sure that that plot is on. I'm going to use plot number 1. If it's not on, then I'm going to make sure that my cursor is on the on, and then I'm going to hit enter. And I'm going to, my type is going to be the first type, which is a scatter plot. And I'm going to be creating this scatter plot using the data that I put in L1 and L2. So I'm going to do a zoom, smack dab in the middle of my buttons at the top, a zoom 9, zoom stepped. Oops, I have a line in there. I forgot. So I need to go on my y equals real quick and clear that out. Okay, let me go back to my graph. There we go. Now, does that look like there's a linear relationship in your data? Does it look like a fairly good, strong, positive, linear correlation? Looks pretty good to me. Okay, so now that I've looked at the data and think that there could be a linear correlation between the stories and the height of the buildings, I'm going to go run the linear regression t-test. So I'm going to go stat, tests, and I'm going to find my linear regression t-test, which is what? F, lin, reg, t-test. And I'm going to run that off of L1 and L2. And I'm going to go ahead and set this beta and rho thing to not equal to. If it's set to anything else, go ahead and set it to not equal to. Because when we actually run linear regression t-tests, we will run them on a not equal to, two-tailed test. Okay? Now, if you don't have y1 in your reg equation, how do you find that variable to put that in? You go to your variables menu, correct? Which is just to the left of clear. You arrow to the right one to the Y variables. And then you're going to hit enter to get to your function variables. And then I'm going to hit enter again to store that in Y1. All right, so I am ready to go. I'm ready to calculate. So I have my X list. My independent variable is an L1. That was the number of stories. My dependent variable, the height of the building, is an L2. Went ahead and set row to not equal to. I'm storing that regression equation in Y1. Okay, so I get a test statistic, 8.0591, which I will use later. A p-value of 0.00004, which I will also use later. Degrees of freedom is 8. And then my equation, I have the y-intercept is 102.4287. That's A. And then the slope is what? 11.75847. Okay. Now, when I graph, hit the graph button, it will graph my scatter plot and my regression equation. All right, so now let's go calculate some residuals. So I'm going to go back to my lists, and I'm going to go over to L3. And this is where it's pretty slick. So I want to calculate the predicted values of Y from my regression equation. So I'm going to put my regression equation in the list L3. So I'm going to arrow up so the L3 is highlighted. And then I'm going to say that L3 is equal to the regression equation. Now, how do I find that? So I'm going to go back to my variables menu, which is just to the left of clear. And you'll notice number 5 is statistics. So I'm going to click number 5. And then I'm going to arrow to the right to equation. And what's number 1? That is the regression equation that you just calculated. So I'm going to hit enter. And you go back in there and you can see that it says L3 is equal to, and it's got the regression equation. However, the regression equation uses the variable X. My X's are in L1. So I'm just going to arrow back to the left, and I'm going to replace the X with L1. So I'm going to go second, 1. So now my regression equation is in L3, and it's going to calculate all the predicted values of the dependent variable from my regression equation. So I'm going to hit enter, and there you go. Okay, so my regression equation for a 57-story building calculates that the predicted value is what? 772.66 feet. So that's what my regression line predicts it to be. What it actually is 1,050. So what's the residual? The residual is the difference between 1,050 and 772. So I'm going to calculate that in L4. So I'm going to go over to my list L4, and then I'm going to go up. And I'm going to let L4 equal the residual. So that is going to be my data value, Y, minus my predicted value, Y hat. So it's going to be what? L2 minus L3? So L2 is my actual data values. L3 are the values calculated from my regression equation. So L3 is all my y hats. So we're going to say L2, second, 2, minus second 3. So those are my residuals. Okay, let's go get out of here. And let's go back, and I'm going to rerun that just for ease. I'm just going to go rerun that test. I could look up each of these values independently, but I'm just going to rerun it. Okay, so S, the number at the bottom of this screen, S equals 132.76488, is actually the standard deviation of your regression. So it is the standard deviation of your residuals. That is what it is. So when the problem says, what's the standard deviation of the residuals? It's 132.764. That's what I didn't do. I didn't graph the residuals. Let's graph the residuals. So this is a graph of the residuals of this problem. And the way you graph the residuals is you're going to graph in your dependent variable the residuals, and in the independent variable, you're going to graph the x's. So let's go do that real quick. So I'm going to do a scatter plot. First, I need to clear the y equals out of there so it doesn't graph it. And then I'm going to go to my stat plot, and I'm going to graph a scatter plot on L1, but not L2, not L3, but L4. So we're going to graph on the dependent axis, the y-axis, the residuals. So we're going to do L4. And I'm going to do a zoom 9. Okay. Now, what's significant about the graph of the residuals? If your data is linearly correlated, you should get just random up, above, and below the x-axis. So it should be very random. It shouldn't be any pattern in it. So you've got a problem in your homework that says which one of these is linearly correlated. If there's any kind of pattern in the graph of your residuals, it is not linearly correlated. It's just got to be scattered, random. Okay? The other thing that the graph of the residuals tells you is possible outliers. And we've got, it looks pretty good, but we've got this point up here that seems to be a little bit farther away from our horizontal axis than any other points. So that point may be an outlier. So it may be something we need to investigate. So there appears to be a linear correlation with what? Maybe one outlier? So they ask you that question in your homework. Does it appear to be linearly correlated from your scatter plot of the residuals? Yes. But it looks like we have one point up there that's a little bit farther from the rest of them. So there may be one outlier. Okay, so what have we done so far? We put our data in our calculator. We calculated the linear regression t-test. We put that equation in Y1. And then we put that equation in L3. And we changed X to L1 so that it would calculate the predicted values from our linear regression test. Then we calculated the residuals. The residuals are our data values, our Y data values, minus our predicted Y values from our regression equation, Y hat. And then we graph the residuals. You graph your X data values on the horizontal axis, and on the vertical axis, you graph your residuals. If there's no pattern, then you're linearly correlated. But we do have this one point up here that looks to be an outlier. Now, how do I test if a point is an outlier? So it says something like this point here. I think that's the one it tells you to look at. And this point here, what was our residual? Go back in your table and tell me what the residual was for your first point. The residual.
Okay.
277, thank you. So the residual for that first point was 277.3. Can you consider that an outlier? Okay, what was our S? What was the standard deviation of our residuals? It was 132.7644. Okay, what's 2 times that? 265 approximately. If the residual is beyond 2 standard deviations of the residual, then it's most likely an outlier. So since 265 is less than 277, so 2 standard deviations is smaller than that residual, or you could look at it maybe this way would be make more sense. 277.5 is bigger than 2 standard deviations. That is most likely an outlier. I mean, that's a really tall building for 57 stories. So that is some kind of anomaly. Is it an anomaly? Legit anomaly? I mean, is it really a 57-story building that's 1,050 feet tall? Or did somebody mismeasure it? Did they make each story instead of 10 feet, maybe each story is 12 feet? I don't know. But anyway, that's something for you to investigate. It is most likely an outlier. Now, do I just delete the data? No. I mean, it's still a data value, but I do investigate it to figure out why I have that outlier. Okay, all right. Let's run some correlation coefficient tests. We perform a hypothesis test of the significance of the correlation coefficient, and we do it just like we've run hypothesis tests before this. We run the tests, we look at the p-value, we compare the p-value to alpha, we reject or fail to reject the null hypothesis. To decide whether the linear relationship in the sample data is strong enough to use to model the relationship in the population. So is our data, the relationship between our independent and dependent variables strong enough that I can use this to predict information about the population? The symbol for the population correlation coefficient is the Greek letter rho. And it's kind of a fancy P, but it's really the Greek letter R. So it's the Greek letter rho. Rho is the population correlation coefficient, which we don't know. R is the sample correlation coefficient, which you calculate from your data. The hypothesis test lets us decide whether the value of the population correlation coefficient is close to 0 or significantly from 0. We decide based on the sample correlation coefficient R and the sample size N. So the null hypothesis test when you're testing the correlation is rho is equal to 0, or that there's no relationship between these two variables. The alternative will be that it's not equal to 0. So that's why we went in there and changed the not equal to, or whatever you had, to not equal to. We're going to run all these tests as not equal to two-tailed test. What the hypothesis means in words, the population correlation coefficient is not significantly different from 0. There's not a significant linear relationship correlation between X and Y in the population. The alternative is that there is a significant linear relationship. So the alternative hypothesis is that the population correlation coefficient is significantly different from 0, or there's a significant linear relationship correlation between X and Y. If there's a significant relationship and the scatter plot shows a linear trend, then you can use that line to predict values of Y for values of X that are within the domain of the X values. What's that mean? It means you can use this line to predict values between your minimum X and your maximum X. You can't really use it to predict values for Y for X's that are beyond the scope of the problem. As a matter of fact, one of your problems says, can I use this to predict? And the answer, I think, on all the problems is no, because the X you're trying to predict a Y for is beyond the scope of the problem. So it needs to be in the domain. It needs to be in the values of X. If there's not a significant relationship, or if the scatter plot does not show a linear trend, the line's not going to be used anyway. If R is significant and the scatter plot shows a linear trend, the line may not be used appropriate or reliable for predictions outside the domain, which is what I was talking about. So it's got to be in the domain within the scope of your problem. Drawing a conclusion, there are two methods. I don't even look at method 2. I used to look at method 2, but you don't have any homework problems using method 2. So you can use your calculator to calculate the correlation coefficient. Excel does this very well. You put your data in Excel and tell it to create a scatter plot and then show you the regression line. It does this very well. So we're going to be using the p-value. That's the only way that we're going to run this test. We're going to use significant level of 0.05. So you're going to compare your p-value to 0.05. If p is less than 0.05, what do? Reject the null hypothesis. If p is greater than alpha 0.05, you fail to reject the null hypothesis. You can choose any significance level you want. 0.05 is certainly not sacred, but that's what we're going to use. You know, how serious is a type 1 error? Well, if the seriousness of a type 1 error is sufficient enough, then lower alpha. Isn't that how you reduce the probability of a type 1 error? You reduce alpha? Okay. Okay, so let's go back to our buildings. So what was our p-value again for that particular regression? Now, I should show you, let me just show you how to look this up. I say that, and it might have changed because I regraphed it. I'm going to rerun it. And then I'll show you that you can look these values up. You don't have to rerun the test every time is what I'm trying to say. Okay. If the P is low, the null must go. So the null hypothesis is that there's no linear relationship between these two variables. The alternative is that there is. That p-value is sufficiently low that we're going to do what? Reject the null hypothesis. There does look to be significant evidence that those two variables are related to each other. They are not independent. They're dependent on one another. If I arrow down, my coefficient of determination is 0.89, so 89% of the variation in Y can be predicted from the variation in X, which is good. That's a good thing, which means that my correlation is better, it's more linear. And R equals 0.94, that's a pretty close to 1. So this is a good linear correlation. So everything points to X and Y being related to each other, or Y being dependent on X. There is a strong linear relationship between the height of a building and the number of stories in the building. All right. Outliers. In some data sets, there are values, observed data points called outliers. Outliers are observed data points that are far from the least squared line. It is possible that an outlier is a result of erroneous data. I'm like, ooh, shiny. Ooh, shiny. I did tell you I was going to tell you how to look up values. Okay, just ran the test and I cleared it. Do I need to run the test again? It's probably just as easy as anything. But all those variables have been stored in your variables menu, in your statistics menu. All those values have been stored in your equation in your statistics menu, variable statistics equations. So for example, R, the correlation coefficient, I can just click on that and hit enter, and it will give me the correlation coefficient. Or, oops, wrong menu, variables, Y variables, excuse me, statistics variables, I will get this right. I can look at the coefficient of determination, which is R squared. So all of those things I can look at. If I want to know the p-value, I'm just going to arrow to test. And number 1 is the p-value. Number 3 is your test statistic. So if you didn't write it down, you can either rerun the test or you can just go here. My p-value was 0.00004. Or I can go back to my variables menu, my stat variables, go over to tests, and my test statistic number 3, my test statistic is 8 point. So you can retrieve all those once you run the test. If you didn't write it down, you can rerun the test, or you can just retrieve them from the variables menu. All right. In some data sets, there are values, observed data points called outliers. Outliers are observed data points that are far from the least squared line. It's possible that an outlier is a result of erroneous data. Other times, an outlier may hold valuable information about the population under study and should remain included in the data. The key is to examine carefully what causes a data point to be an outlier. How can you identify? You could just look at the scatter plot and guess. However, we would like some guideline as to how far away a point needs to be in order to be considered an outlier. A rough rule of thumb is if it's located more than 2 standard deviations from the best fit line, it's probably an outlier, which is why when we looked at the data for the stories of the buildings, the stories and the height, that first building, the residual, the distance it was from the best fit line, that's what a residual is. It's the distance that data value is from the best fit line. It was more than 2 standard deviations from the best fit line. That made it a potential outlier. Okay? The standard deviation used in the standard deviation is the standard deviation of the residuals or the errors, and that's what your test calculates. We can do this visually, or you can let your calculator do this for you, which is what we're going to do. Excel does this very well too. If we were to measure the vertical distance from any data point to the corresponding point on the line of best fit, that distance is at least 2 standard deviations. We would consider the data point to be too far from the line of best fit. So what we need to do is we need to find and graph the lines that are 2 standard deviations below and 2 standard deviations above the regression line. If you have any actual data values that are outside those 2 lines, those are potential outliers. If you delete an outlier as a researcher, you have to tell everyone that you did it, and you have to tell them why. Let's say you know for a fact that that first building was mismeasured, or maybe the building manager, the building owner just gave you the wrong information. Can I delete that outlier? Yes, if it's an erroneous data value, I can delete it, but I have to tell people that I deleted it. And this is the reason why. If you knew, for example, that first building wasn't really 1,050 feet tall, you find out later it's 900 feet tall, you could correct your data. Okay? So if you have any data values that are above or below lines that are 2 standard deviations from your regression line, so here is your regression line in blue. The 2 yellow lines are the regression line plus 2 standard deviations, and the regression line minus 2 standard deviations. If you have a point that's beyond those 2 lines, it's a potential outlier. Okay. So let's put this data in our calculator. So you're going to put the first coordinates. You're going to put the first coordinates in a list because those are your X's. And you're going to put your second coordinates in a list because those are your Y's. So I'll give you a second to do that. We got it in? Because I need to go put it in. Are we good? One, two, 2, 3, 4, 4, 5, 6, 7, 7. Okay, what was our Y2s? I mean our Y values. 5, 7, 6, 9, 12, 13, 18, 19, 12, and 21. Does that look good? Okay, so I'm going to first go into my Y equals and clear out anything I have in there. So I'm going to clear out that previous regression line. And then I'm going to go to my stat plot. And I'm going to graph a scatter plot based on L1 and L2. Second, 2. And to set my window, I do a zoom 9. Okay, so now I have what looks to be a fairly good linear relationship. I'm kind of curious about this point. So let's go run the linear regression t-test. So I'm going to go stat, tests, linear regression t-test. And I'm going to store that regression equation in Y1. So if you don't remember how to do that, we go variables, Y variables, function number 1. Okay, now let's calculate. All right, so now I can go look at my graph. And it will graph my regression equation along with my scatter plot. So now what I want to graph is the regression equation plus 2 standard deviations and the regression equation minus 2 standard deviations. So I'm going to go to my Y equals. And I'm going to go down to Y2. And in Y2, I'm going to graph that regression line, Y1, plus 2 standard deviations. So this is how I do it. I go to my variables, my Y variables, my function variables, Y1. So I hit enter. So now I have Y1 in Y2. Y2 equals Y1. I'm going to add to that 2 times the standard deviation of the residuals, S. So how do I find that? I go to my variables, my statistics variables, my equation variables. Actually, I need to go over to my test. Where do I need to go? I have to go to my test because that's where S is stored. So S is stored under tests. So I hit enter and I have Y1 plus 2 times the standard deviation of the residuals. Now we're going to subtract 2. So we go down, variables, Y variables, function number 1, minus, and someone asked me the other day, wouldn't it be nice if there was a cut and paste feature for calculator? Wouldn't that be nice? 2 times S. So I got to go find S again. So I go to my variables, my statistics variables. I go over to my test and I find S. Now, when I hit the graph button, it's going to graph my scatter plot, my regression equation, and plus or minus 2 standard deviations from my regression equation. So do you have an outlier? Where's it at? Over there at the end? So how do I figure out what that point is? Just arrow over there. Well, let me arrow over there. What is that point? Is that the 712? So what's considered the outlier, the point 712? Bless you. So it looks like this point right here. Stop helping me. Looks like this point right here is my outlier. So it says, remove the outlier and recalculate the line of best fit, and then find the value of y hat when x is 10. And your calculator can do all this. Okay, so I'm going to go back to my data and I'm going to delete that point from my list. I'm going to delete 712. So we're going to go back to our calculators. We're going to go to our lists. And we're going to delete the 712. Now I need to delete it from both lists. So I need to delete the 12, delete, hit the delete key, and then I need to go and delete the 7, delete. Okay, now we're going to do this all over again. So I'm going to go oh, Lisa, what are you doing? I don't know what I'm doing. All right. So we're going to go stat tests. We're going to run the linear regression t-test again. And we're going to store that regression equation in Y1 again. And now when I go look at my graph, I'm going to do a zoom 9. That point should be gone. And you noticed it recalculated the everything for me. So it recalculated my standard deviation of residuals, or recalculated my lines, and did all that. Okay, from my regression equation, can I calculate y when x is 10? And the answer is yes, because that is within the scope of my problem. My x's go from what? Well, maybe not. X's go from 0 to 7. So maybe 10 is not appropriate to calculate the y hat for it, but we're going to anyway. Okay, I'm going to show you the boo-boo, and then we'll show you how to fix it. Hopefully it'll boo-boo. Okay, so how do you calculate a y value for a given x? Your calculator can do this. So in your calculate menu above trace, do you see that calculate menu? Number 1 is value. That is a y value for a given x. So it will calculate y hat for you. So when I hit enter, x is what, 10? It gave me an error. Why did it give me an error? Do you know? The window didn't go out that far. So what do I need to do? I need to adjust my window so that it goes to at least x is 10. So when I set the window using zoom stat, it sets the window to my maximum x value, which was what, 7? So it's going to set it a little bit more than 7. So since I'm calculating a value that's beyond the scope, I need to adjust the window. So how do I do that? So I go to my window menu, which is just next to my y equals, and just adjust that Y max to at least 10. I'm going to use 11 and then regraph it. And now we should be good to go. So we're going to go second trace to our calculate menu. We're going to calculate a Y value when X is 10. And that is what? 30.732. So the predicted value when X is 10 is 30.7324 based on our regression equation. Okay, we're going to go ahead and do this one because this will do everything for us. So we'll do everything. Draw a scatter plot, calculate the least squares line, draw the line on the scatter plot, find the correlation coefficient, is it significant, and then what is the average CPI for the year 1990. So put X in a list, put Y in a list. I'll give you a minute. Are we good? Still working on it. I'm surprised how speedy some of you are getting this data in. Impressive. I said, when I give you 1 minute, I wasn't exaggerating. That was almost exactly 1 minute. All right. So we're going to do a scatter plot. We're going to run the t-test on it. We're going to do all of that. So the first thing I need to do is I got a whole bunch of stuff in here. I need to clear all that out. So all that hard work of getting all that stuff in my Y equals, we're going to clear all that out. Okay. Now I have my data in L5 and L6. That's just because I didn't want to have to put all that data in while you were sitting here and watching me. So I'm going to do my scatter plot and everything off of L5, L6. Wherever you put it, that's what you're going to use. Okay, so let me get out of here. I'm going to run a scatter plot on that data. I put it in L5 and L6. And we always start with a scatter plot because if it doesn't look like anything, we're not going to bother going any further. Okay, so I'm going to do a zoom 9, to fit my window to my data. I don't know how linear that is. Looks like it might fit some kind of other model, but we're gonna go with it. Okay. So let's go to stat, tests. Let's run the linear regression t-test on our data. I put my data in L5 and L6. Wherever you put your data, that's what you're going to run your test off of. And I'm going to store this. I'm going to go ahead and leave the not equal to and store this in Y1. And remember, how do we get to Y1? Variables, Y variables, function number 1. Okay, let's calculate. All right, so my test statistic is 6.0939. The p-value is very small. So it appears to be a linear relationship between these two variables. The equation that models this data is negative 3,204 plus 1.66245x. Let's go ahead and go down and look at R and R squared. So R squared, the coefficient of determinations, 76%. And R is what, 0.8694? Okay, let's go ahead and graph. So there is the graph of my regression equation and my data. Okay, so what's the CPI in 1990? And I should be able to calculate that. Oh, is the correlation coefficient significant? That p-value is very small, correct? So yes, the correlation coefficient is significant. Because the p-value is so low, we're going to reject the null hypothesis that there is no relationship, no linear relationship between this data. It appears to have a linear relationship. Okay, so we can calculate the CPI for 1990 just by going to second trace, go to our calculate menu. The value for X is what, 1990? So the consumer price index in 1990 was approximately 104. As predicted from this regression equation. All right, last but not least. So what are we going to be doing Thursday? Review? Are you game? Okay, this is a problem in your homework. This is question 12.6, number 4. And this is data that comes from Excel. So this is not your calculator. This is how Excel would present your data. Okay, so you got a scatter plot. And then you got some stuff over here. So in this table, they actually give you the coefficients for the intercept and the risk. That's the slope. So what they're comparing is, what are we comparing? Height to your risk size. So that's what this data represents. And so the equation that fits this data would be for every inch your risk gets bigger, your height goes up by 4.6 inches. That's what this means. So the equation that models this data is 4.5964x plus 38.4771. So that is the slope, and that's the y-intercept. Okay? So the equation of best fit is 4.5964x plus 38.771. Okay, what's the correlation coefficient? Well, the correlation coefficient is R. And the way it's presented in Excel as it's called multiple R, and it's capitalized. But that is your correlation coefficient. What's your coefficient of determination? Well, that's R squared. Now, use the equation of best fit to predict the height of a person with a wrist circumference of 6 inches. So you take the wrist 6 inches, you multiply it by the slope, you add the y-intercept. So it's 6 times whatever that number is plus whatever that number is. One of the points in the scatter plot is 6.47.75.1. What's the residual? Well, the data value y is 75.1. So you calculate the residual how? You use the 6.4 in your equation, calculate the y hat, and then take the difference. What's the mean wrist circumference for this data was 6.997. Predict the mean height, plug it in and find the height. Standard error of the estimate they actually give you, the standard error is 3.4469, which is the standard deviation of the residual. So they just use a different word for it, but it's in this table. So all the information's in these two tables. It's just different than what we've been presented with prior to this. Are there any questions? All right, we will see you Wednesday, and we'll look at the exam for review.